Welcome to the Ready Academy. Tools for teaching, tools for learning, tools for life. In this video book, we cover simple machines. This content was produced with AI assistance and reviewed by a human instructor. We'll continue with the pulley. Fixed, movable, and combined. Suppose you need to haul a 2,000 Newton piano to a second-story window, a load that no single person can lift directly. Throw a rope over a ceiling hook and you can pull downward using your body weight instead of pulling up. But you still need 2,000 newtons of pulling force because the hook only changes direction. The question this section resolves: how do you configure a rope and wheel system so that a much smaller pull lifts a much larger load? And exactly why does adding more rope segments reduce the required force? A pulley is a grooved wheel mounted on a fixed axle. Rope runs in the groove, and the wheel spins freely so the rope can redirect without losing energy to sliding friction. Three cases matter: the fixed pulley, the movable pulley, and the block and tackle. A fixed pulley is mounted to a stationary support, a ceiling beam, a cliff edge, a crane jib, and its only job is to change the direction of the applied force. One end of the rope holds the load. You pull the other end in whatever direction is convenient, usually downward, so gravity and muscle work together. Because the rope length on the load side and the rope length on your side both change by the same amount for any movement, the work conservation, equation 2.2, requires the effort force to exactly equal the load force. A fixed pulley has an ideal mechanical advantage of 1. It is a direction changer, not a force multiplier. A movable pulley is attached to the load itself rather than to a fixed support. It travels upward with the load as you haul. One end of the rope is anchored to a fixed point. The rope then passes under the movable pulley and back up to your pulling hand. So the load is supported by 2 rope segments simultaneously. Each segment carries half the load, so you pull with only half the force needed to lift the load directly. The price, as always, is distance. To raise the load 1 meter, both rope segments must shorten by 1 meter each, so you must pull 2 meters of rope through your hands. A movable pulley has an ideal mechanical advantage of 2, the simplest true force multiplier. A block and tackle combines 1 or more fixed pulleys in a top block with 1 or more movable pulleys in a bottom block, threading the rope back and forth to create N rope segments running between the 2 blocks. Equation 5.1. The ideal mechanical advantage of a block and tackle equals N, the number of rope segments supporting the moving block. N is the whole answer. Count the rope segments carrying the load, and you have the force multiplication. The logic is the work conservation argument applied once more. N rope segments share the load equally, each carrying load force divided by N. To raise the load 1 meter, every one of those N segments must shorten by 1 meter, meaning you must pull N meters of rope. Work in equals effort force times N meters of rope pulled. Effort force equals load force divided by N. Multiply them and the N's cancel, leaving load force times 1 meter. Work in equals work out, exactly. The geometry, how many rope segments you create, is the whole story. Animation 5.1. In a 4-rope block and tackle, the rope feeds continuously through the system. A counter tracks how much rope is pulled on the effort side versus how far the load rises. When 4 meters of rope have been pulled, the load has risen exactly 1 meter. The 4-to-1 mechanical advantage made visible as motion. Figure 5.1. 3 pulley diagrams in a row. At left, a single fixed pulley attached to a ceiling beam, rope over the wheel, a load hanging from one end, and a hand pulling down on the other, labeled fixed pulley, IMA equals 1. Both rope ends move the same distance, so no force is gained. At center, a single movable pulley attached to the load, one rope end anchored to the ceiling, and the other end pulled upward, labeled movable pulley, IMA equals 2. The load is cradled by 2 rope segments, each bearing half the weight. At right, a block and tackle with 2 pulleys in the top fixed block and 2 in the bottom moving block, 4 rope segments visible between the blocks, labeled block and tackle, IMA equals 4. Count the segments, and you read the force multiplication directly. Figure 5.2. A close-up annotated view of a 4-rope block and tackle lifting a 400 Newton anchor. Each of the 4 rope segments running between the upper fixed block and the lower moving block is labeled 100 newtons tension, and the hauling hand is marked 100 newtons effort, showing that the 4-fold load is shared equally across the 4 segments. A vertical double arrow at the side of the diagram shows that to lift the anchor 1 meter, the user must pull 4 meters of rope. Every meter of height costs 4 meters of effort travel. A caption reads, "Work in equals 100 newtons times 4 meters equals 400 joules, equals workout equals 400 newtons times 1 meter," confirming that the 4-fold force reduction is exactly compensated by a 4-fold increase in distance, and no energy is created or destroyed. Real pulleys lose efficiency multiplicatively. An ideal block and tackle assumes the rope slides frictionlessly over every wheel. Real pulleys do not. Every sheave, the grooved pulley wheel on its axle, introduces a friction loss as the rope bends over the rim and the axle turns against its bearing. If each sheave has per sheave efficiency, eta, twice, and n sheaves are in the system, the losses compound. The total system efficiency is approximately eta, x raised to the power n. 6 sheaves each at 95% efficiency deliver roughly 0.95 to the 6th power, which is about 73.5%. Friction has already consumed more than a quarter of the input work. Beyond 6 or 8 sheaves, adding another pulley adds more friction than it removes from the required effort, and the actual effort force begins to rise rather than fall. This is why practical rigging seldom uses more than 8 sheaves, and why regular lubrication of sheave bearings matters so much. Piano lift. A 2,000 Newton piano must be raised to a 2nd-story window using a block and tackle with 6 supporting rope segments. Each sheave has a per sheave efficiency of 95%. Find A, the IMA, B, the system efficiency, C, the AMA, D, the required effort force, and E, the length of rope that must be pulled per meter of piano height. Step 1. Find the ideal mechanical advantage. By equation 5.1, the ideal mechanical advantage equals the number of supporting rope segments. IMA equals N equals 6. 6 rope segments share the 2,000 Newton load, so in the ideal case, each carries about 333 newtons, well within one person's pulling capacity. Step 2. Find the system efficiency. Raise the per sheave efficiency to the power of the number of sheaves. Eta approximately equals 0.95 to the 6th power, approximately 0.735. Friction in the 6 sheaves consumes about 26.5% of the input work as heat, leaving 73.5% to do useful lifting. Step 3. Find the AMA. Multiply the system efficiency by the IMA using equation 2.7. AMA equals eta times IMA 0.735 times 6, approximately equals 4.41. Friction has reduced the effective force multiplication from 6 down to about 4.5. Step 4. Find the effort force. Divide the load by the AMA. FE equals FR divided by AMA. 2,000 divided by 4.41 approximately equals 454 newtons. Roughly, the force needed to support a 46-kilogram suitcase lifts a 2,000 Newton piano. Step 5. Find the rope pulled per meter of lift. For every meter the piano rises, each of the 6 supporting segments must shorten by 1 meter. Therefore, 6 meters of rope must pass through the hauler's hands for each meter of piano height. That is the distance trade-off of a 6-segment tackle. IMA equals 6. System efficiency approximately 73.5%. AMA approximately 4.41, effort approximately 454 newtons, 6 meters of rope per meter of lift. Elevator cable tension. An elevator cabin is suspended by 4 supporting rope segments. A counterweight exactly cancels the weight of the empty cabin. A 700 Newton passenger steps inside. Assuming ideal conditions, what cable tension must the motor apply to lift the cabin at constant speed? Pause the video now and give it a try. Rescue rigger. A rescue team sets up a 5-to-1 block and tackle to haul a 980 Newton injured climber up a cliff. Each of the 5 sheaves has an efficiency of 90%. Part A. What is the ideal effort force? Part B. What is the system efficiency and the actual effort force required? Part C. To raise the climber 8 meters, how much rope must the team haul? Pause the video now and work through all 3 parts. A fixed pulley has an IMA of 1. It doesn't save any force. Why would anyone ever use one? Give 2 distinct practical reasons and an example for each. That wraps up the pulley. Next up, Section 6, the inclined plane. If you found this helpful, like and subscribe, and support the channel.